Greetings, my name is Ryan Nix. I'm a solutions architect with Amazon Web Services. Joining me here today is Eduardo. Eduardo, say hi.
Hello everyone, I'm also a solutions architect with AWS. Nice to meet you all.
Now, Eduardo, previous life, you've worked at a couple of companies in Europe using application platforms such as OpenShift, is that correct?
That's correct. We had a large platform implemented where we have a lot of workloads deployed onto OpenShift. And one of the main problems we ended up with was a lot of data replication across AZs.
Okay, right. I'm glad that you've run into that because that's exactly what I wanted to talk to you about. A lot of my customers are coming to me and they're saying things like, we utilize an application platform. Some of them are using OpenShift, some of them are using other versions of Kubernetes, some of them are using, whatever product or technology. Right. They migrate that from on-premises onto AWS, and then they start noticing some interesting behaviors. And I'd like to take a moment to dig into this from an architectural perspective, as well as from a, what is actually happening within those products and technologies in the background. So let's take a second and look at a stereotypical, let's take OpenShift as an example here. So when we bring OpenShift onto AWS, one of the things that we do is we take the resilience model that OpenShift provides and we combine it with the resilience model that AWS provides for customers. So let's look at the AWS side very quickly. What we're looking at over here is one AWS region, so we can get close to our customers. And within that region, we've created a VPC or a networking infrastructure, and we've created subnets that span one of each of the availability zones. Eduardo, give me a 30-second rundown on what is an availability zone and why do we care about them.
Right, so if you're looking for highly available applications deployed on AWS, our regions are comprised of different availability zones, and there are the locations where our data centers reside, and they are separated from each other over an important distance so that you gain the benefits of high availability. And they also have dedicated power and utilities, so that in case one availability zone fails, you still have other availability zones where you can run your applications without having a full outage or minimizing impact to your workloads.
So we don't think of the entire AWS region as a data center. It's really the availability zone itself is the closest construct that AWS has to a data center. In truth, it's not a data center.
It's a group of data centers.
It's a collection of them. But we treat them as something that is going to fail as a failure point. So if an AZ is impacted by an event, we treat everything in that AZ as an impacted sort of blast radius, if you will. And this is one of the things that my customers struggle with when they come from on-premises. They're like, I need to have multiple regions. So I need to build out my infrastructure in, say, the US East, and I need to do it again in US West to meet a multiple data center requirement, and that's not entirely true. I could just make sure I've got my workloads running in each AZ. Coming from an OpenShift standpoint, when you deploy OpenShift onto AWS, whether this is self-managed OpenShift or whether this is something like a managed version like ROSA, for example, you're going to see some common ground. Firstly, we're going to take that OpenShift control plane, and the OpenShift control plane in itself is resilient. And how OpenShift achieves this is it runs on top of EC2. So you're going to see here is an EC2 instance over here. There's another one over here in a different AZ and another one over there. And these are my OpenShift master nodes. That is the OpenShift API endpoints. It's the OpenShift control plane. And why there's three of them is if something happens and we lose that EC2 instance or that virtual server, there are another two up and running in the other two AZs. There is replication between those nodes to make sure that the etcd database is in sync between them. So immediately what we run into is from this, well, let's do it over here. From this node to that node, we do have some degree of replication of etcd to make sure that my control plane is. So even if you just deploy OpenShift and you do nothing with it, it periodically will synchronize those control plane nodes so that if you lose one, there are two other copies. If an entire availability zone, for whatever reason, is impacted, my OpenShift control plane is still up and running. Likewise, we have another layer over here, these EC2 instances sitting over there as the infrastructure layer. I think the most important thing there is probably the OpenShift router layer.
Yes.
It's a reverse proxy of sorts. So we're going to put in a router layer.
This is essentially what lets the outside world reach your applications inside OpenShift.
Absolutely correct. So behind that router layer, we're going to have a collection of EC2 instances that are compute nodes, or what OpenShift refers to as worker nodes, and my actual applications, my Kubernetes pods and my application workloads are running on there. You cannot connect to those directly. You are going to come through some sort of entry point. So I'm assuming AWS load balancer somewhere,
Yes,
fiddling around here. Where would that sit typically?
So this would sit on your subnets in either a public VPC, if you public subnet if you're exposing your cluster to the public internet, or it could be on a private subnet if this is a private cluster setup. But it would essentially have a load balancer here that would be talking to your infrastructure nodes, to your OpenShift router, to redirect the traffic to your pods.
Okay, so there's a couple of things here. One of the things you mentioned was public subnets. In this design, you can see all of our subnets are private. So this means that in this implementation, nothing's being exposed to the outside world. If my customer did have a requirement to expose this externally, this would probably link through some sort of AWS transit gateway,
Yes,
and then re-expose it some other way.
A very common pattern is for customers to use an egress VPC where they can control traffic and keep their cluster, OpenShift cluster, with the workloads in a private setup that they can only access either from their on-premise setup, or they can have a better control of what they're exposing to the public internet.
Okay, now you've done something very interesting over here, or at least it's interesting to me. Normally we would have something like Route 53 as a DNS provider, and that would resolve to my load balancer. Then my load balancer would connect to something in AZ, connect to something else in my AZ, and everything would stay in one availability zone. But what you've done here is very cool. Traffic comes into my load balancer and it goes to the OpenShift router layer. The OpenShift router layer has no construct of these availability zones. So it simply takes that customer connection and sends it on to one of the available compute nodes. And it could very realistically send information to a EC2 instance or a compute node in one availability zone, and it could take the next connection and send it to one in a different AZ and one in a different AZ.
Yes.
So you do see cross availability zone connections over here. And this is going to incur some degree of cross availability zone costs. So you are going to see data transfer related to that. Now, some of my customers say, I don't want that, and unfortunately, there isn't an affinity concept. There isn't a way that I can deploy OpenShift and say all connections will run in there. Well, there is, to some degree. You can take your applications and put them in one AZ.
You can use pod affinity and node tainting to put them on one AZ, but then you lose the concept of using high availability across different AZs.
Well, you would still have high availability within the context of OpenShift. So, for example, if you had multiple EC2 instances here and all of your workloads running there, you would have resilience from an OpenShift perspective.
Yes.
But you lose the concept that if something happened to this availability zone,
you will have downtime until your applications are recovered on another AZ.
Or you would have a very manual reaction to that in terms of shifting things to another availability through OpenShift. So being able to detect that, manually respond to it, really the shiny things happen when we combine these availability constructs. So what we're talking about here ultimately is the trade-off of data transfer and cost in relation to the resilience model. Let's make this worse.
What if you have applications on OpenShift that need to persist data to disk?
Right, so when we talk about persistent data, everybody quickly jumps to Amazon's EBS, and we got a little bit of a problem over here. EBS attaches volumes to EC2 instances in a single availability zone. So if my workload moves to a different AZ, I can't interact with my storage. I can't interact with that EBS volume. So really what I'm looking at here is something that is shared or spans multiple availability zones. And there's a couple of products on the market over here that could be very interesting. I need a storage layer. There we go. Okay. So what we're going to do is we'll add in something like, this could be Ceph, this could be OpenShift Container Storage Services, very old name. This could be OpenShift Data Foundation, which is the slightly newer name. It's now being rebranded to IBM Storage Fusion, but in essence, this is very similar to most shared storage technologies. There's an EC2 instance that is deployed in each availability zone, and there are AWS EBS volumes that are attached to that compute or that storage node, and then we present that storage to my application. So workloads here in AZ1 can interact with a storage node over here, likewise over there. Now the catch-20 here is, in order for me to cater for my resilience model, I need the data to be persisted or duplicated in all three availability zones.
Correct.
How does that typically happen?
Well, you're going to have data copy from these different EBS volumes between the different AZs. So you're going to have data replication happening here. And you also have to keep in mind, not only for failover, but if you also have an active pod distribution across the AZs for your workload, you're also going to look at replication of data between these volumes on the different AZs to make sure that the data is available to the pods across the AZs.
So again, this is a resilience, but what typically happens is this would be a synchronous replication, which means new information would be written into the storage node. That storage node would write it to the EBS volume, then replicate it to the other AZ, replicate it again to the other AZ, then only come back and signal that that data was written correctly. Right. So we've got two things here. There's a performance consideration depending on how far apart these are. In an AWS context, these availability zones are geographically close enough to each other where the latencies are relatively minuscule. You're not going to see a dramatic difference from one AZ to the other. The churn of the data, how quickly that data changes, and the sort of volume of the data that is changing does become a consideration if you're looking at huge data payload changes. And then, of course, we do run into the question of that data is going to incur data transfer costs between that. So just to understand here, this is purely how OpenShift and how technologies such as the storage layer are implemented and how they achieve their resilience and the considerations and ramifications of that. It's not a bad design. It's really the ultimate discussion of if I want a highly available, resilient solution, I am going to pay a little bit for it.
Yes. And it also depends on the architecture of the applications that you're running on OpenShift, because you can be looking at different storage options for OpenShift on AWS that can help you reduce these costs, at least for the data replication across AZs. That's
a very valid point. Not all of my data is going to go into persistent storage. One of the customers I worked with was an airline out of Singapore, and one thing that they did very well was, wherever possible, get rid of persistent storage. Move things such as relational database data out to something like AWS RDS, and then you're not dealing with managing the storage here. NoSQL environments going to something like AWS DynamoDB. Your caching, your queuing mechanisms could also be AWS managed services where you don't worry about the storage layer. So think about the storage layer as do I absolutely need this or don't I? Could I potentially refactor my application to get around this?
And also think about the types of data that if you must persist data on OpenShift, think about the type of data, because you will be looking at different options for the storage layer. That can help you mitigate those costs as well.
What if we take the storage layer and we replace it? If we didn't implement a storage solution that utilized a EC2 instance and attached storage in each environment, we potentially could get away from the replication. AWS EFS and AWS FSx NetApp ONTAP. Those two solutions take a slightly different approach. They still utilize the construct of EC2 instances in each AZ, and they still have the concept of some form of attached storage. So there is going to be storage attached to those. However, this doesn't happen in the customer's account. It happens in a back-end platform catered for AWS. So in a product service team account, you see the underlying storage. What the customer gets in their account actually is an endpoint.
An endpoint, yes.
Okay. So the endpoint exists over here, and my application workloads talk to the endpoint. And because the endpoint is interacting with us, and these systems are still replicating with each other, but the replication takes part not in my customer's account, but somewhere else, we don't have this replication cost in the same way as we see with other storage systems. And this becomes a very, very attractive way to sort of get around this problem.
Well, and this for Amazon EFS and FSx, like Brian said, but if you're also dealing with applications that are handling flat files or blobs or anything like that, you can even consider using S3. And then you also get rid of the replication because it's a regional service.
Coming back to our getting rid of persistent data.
Yes. Okay.
So just to summarize, what we see is with solutions like OpenShift and AWS, because of the combined resilience model, the way in which OpenShift functions, you are going to see some data transfer. Some of it is manageable. You can move things such as your storage layers and take advantage of other managed AWS storage services. You can get rid of some of the persistent storage, but you're never going to get rid of all of it. You are going to have to deal with the resilience model and the data replication related to your control plane. You are going to have some interaction of data transfer related to how the OpenShift router allocates workloads. And if you are utilizing a storage solution like this, you are going to have to live with the consideration that I have replication related to the resilience model. Eduardo, thank you very much for joining me. Always a pleasure having you here.
Thank you. Thank you, Ryan, and thank you for joining us. And we are here to help you. Understand. We can help you dive deep into the workloads you're planning to run on OpenShift, and then understand what's the best storage possible for those types of workloads, so that you can optimize your OpenShift infrastructure and also all the costs of what Ryan said about cross-AZ replication. Thank you.